This is the first of two films about static electricity, Electrostatics. We'll be looking at some important applications of electrostatics in commerce and industry and in everyday life. But first of all, let's look at some laboratory experiments which show us some basic principles of electrostatics. When this plastic rod is rubbed with a clean, dry paper tissue, it becomes electrically charged. In fact, it's negatively charged. We hang it up so that its weight just balances the weight of the thin wooden stick pivoted on a razor blade. Now let's rub another plastic rod, just like that one, with a clean tissue. It repels the first one, because each plastic rod has the same kind of charge. They're each negative, and like charges, repel. Now let's see what happens if we try the tissue. It attracts the rod because it has gained a positive charge. And unlike charges, positive and negative attract each other. What happens when we create static electricity in this way is that one body acquires a negative charge while the other becomes positive. We believe that tiny charged particles called electrons have passed from one body to the other, causing the bodies to become positively and negatively charged. All matter contains electrons. If we heat up a metal filament in a vacuum and connect it to the negative lead from a high voltage supply, electrons stream off from it. They produce a spot of light on a fluorescent screen at the end. This is a collector into which we're going to steer the electrons. It's connected by this wire to the plate at the top of a gold leaf electroscope. Because the electrons are charged particles, they can be deflected by a magnet, and we can guide them into the collector. Their charge passes up the wire to the electroscope, causing the gold leaves to part, to diverge. Let's watch that again. When we rub an ebonite rod with fur, the rod becomes negatively charged. Hold it near the electroscope and look, the leaves move even further apart. The negatively charged rod seems to increase the effect caused by the electrons. But a glass rod, which becomes positively charged when rubbed with silk, causes the opposite effect. It cancels out the effect of the electrons, and the gold leaves collapse when it's held near. Let's recap. The electrons charge up the gold leaf, causing it to diverge. A negatively charged rod makes the leaves diverge even further. A positively charged rod causes them to collapse. So what is the charge on these electrons? The tiny particles present in everything and streaming off from this hot metal. Are they negatively charged or positively charged? Think it out. And if the plastic rod becomes negative and the tissue positive, which has gained and which has lost electrons when we rub them together? When something becomes electrostatically charged, it's always because it has either gained or lost electrons. Work out from the experiment you've just seen whether electrons are positive or negative. Then you'll understand what's happened whenever something has become positive or negative in some electrostatic process. Here's a demonstration of an electrostatic process you may have felt for yourself. When you rub the dry soles of your shoes on a dry nylon carpet, you create electrostatic charge, which can build up to a high voltage. This girl's connected up to a voltmeter, which reads in thousands of volts. The charge builds up on her and on the carpet. Here's how she's connected to the voltmeter. Nearly 4,000 volts. If she now touched, say, some metal object, she'd feel a short, sharp shock as the charge passed from her to Earth. Not dangerous, because the current would be very small. If she now stands still, the charge leaks away slowly and she feels nothing. Many of you must have experienced this sort of thing in warm, dry rooms when you walked across a synthetic carpet, then touched a door handle or something. It's one of the nuisances of static electricity in modern life. Here's something more important, more useful anyway. This is a sheet of plastic material. Let's pretend to write on it by rubbing it with a finger in a nylon glove. We don't see anything, of course. But we can use the negative static charge built up on the plastic to reveal what's been written. The box contains a mixture of red lead and sulfur. When they're shaken out, the two powders become electrostatically charged by friction as they rub against each other. The red lead positive, the sulfur negative. The positively charged red lead particles are attracted to the negative charge created when we rub the sheet with our finger. And the writing becomes visible. This is the basis of a very important method of copying documents and so forth in offices and other places. It's called xerography, and here's a modern machine in action. Let's see how it works. Here's a paper we want to copy. It's put in the copier, and a system of mirrors and lenses produces an image of the sheet on the most important part of the machine, which is here inside. Running around these three rollers, there's a continuous belt made of a very special material, as we'll see. Let's look at it, pulled out from the machine. Here it is. It can be given a positive electrostatic charge when it's running in the dark inside the copier. Suppose this is a part of the belt, looking down on it. The little pluses represent its positive charge. Let's concentrate on just this section of it. Here's something we want to copy, a large X on a white sheet of paper. Its image is reflected onto the belt. Now, the belt is made of material which conducts electricity when light is cast onto it. The white portions of the paper reflect light onto the belt, and the charge leaks away through the belt from those areas, because they're now electrically conducting, leaving a positive charge in a pattern corresponding to the black portions of the original diagram. If the belt's now dusted with a negatively charged powder, this sticks to the positively charged area, like this. We've now got a copy of the original in black powder on the belt. We've got an image of the thing we're copying, which we can see. When this page is copied then, the white areas, such as these, reflect light onto the belt so that it loses its static charge in those areas. Most of the sheet, in fact, is white, so charge will disappear from the corresponding region of the belt. But where there are black letters or lines, these reflect no light onto the belt and the belt keeps its positive charge. This is the part of the machine where the black powder, given a negative charge, sticks to the positively charged parts of the belt as it passes over the brushes. Here's some of the powder. It's actually coated onto tiny metal balls, from which it's smeared onto the belt and sticks only where there's positive charge. The belt then looks like this. You can see a reverse copy of our document traced in black powder sticking to the belt. The moving belt is made to press against a blank sheet of paper and transfer the powder to the paper. Here's the original and the copy. But this wouldn't be much good because the powder is easily rubbed off, as you can see. So in another part of the copier, the copies are heated, which makes the powder really stick to the paper. The belt goes round and round, being charged, receiving a reflection of the sheet we're copying, picking up powder, transferring this to paper, then going round again, so that a modern machine like this can go on and on making good copies at a tremendous speed. And it all depends, in the end, upon the principles of electrostatics. Now for a very different application of electrostatics. First, let's see a laboratory demonstration. These leads are used to apply a very high voltage across this apparatus. The outside of this metal chimney is earthed, while the positive lead from the high voltage unit is clipped to a terminal which connects with a couple of wires passing down the middle. The wires go down here, but you can't see them very clearly at this stage. When we switch on, we'll now have a big potential difference between the wires passing down the middle. Across here. Beneath the chimney, there's a hot plate. If we put some ammonium chloride on it, it sublimes off, and its white fumes pass up. And out at the top. Now let's switch on the high voltage unit and turn it up so that we're applying about 21,000 volts. The smoke stops. Although it's still passing in at the bottom, turn off the high voltage and the smoke emerges again. This is a model of an electrostatic precipitator which can be used to cut down industrial smoke. Watch it again. The forces produced by the electrostatic charge applied to the central wires cause neutral atoms to lose electrons and become charged ions. These ions are repelled by the positively charged central wire towards the outside wall. But they tend to attach themselves as they do so to the tiny smoke particles and carry these to the outside, as you can see. So we've got a very convenient way of preventing smoke particles from getting out into the atmosphere. Electrostatic precipitators are used in many industries. Many electricity generating stations use them, like this huge coal-fired plant at Fiddler's Ferry in northwest England. The tall chimney is just a chimney. It's not itself the precipitator, as we'll see. Powdered coal is burned in the furnaces to produce heat to make steam for the turbo generators. We'll explore some modern power stations in another of these films. But just now, let's concentrate on what comes out of the furnaces. Heavy ash falls to the bottom. The finer ash and smoke particles are carried up through flues. And if it were allowed to escape into the air, this would cause great pollution. Big precipitators are used to prevent this. You can see the great tube taking furnace gases to a precipitator, like an enormous square box, inside which the waste gases pass between electrically charged plates, which collect the smoke particles. Automatic mallets strike these plates, causing the powder to fall off into a container at the bottom. The cleaned gases then pass along to the chimney stack and are discharged into the atmosphere. There's a long line of precipitators, as you can see, dealing with all the power station's furnaces. There are 8 coal-burning furnaces at this power station, and each has 2 precipitators. There's the stack, 650 feet high, which takes the clean gases which have passed through the precipitators. Here at the top of the stack, we find another important application of electrostatics, something you've probably all noticed on high buildings. Lightning conductors. Enormous electrostatic charges can build up in certain types of cloud, until the very high potential difference between cloud and earth causes the air's insulation to break down. We get a flash of lightning. Lightning conductors provide a safe path to earth for the tremendous energy of the flash, so that the building itself isn't struck and damaged. See how the lightning conductors at the top of this stack are very thoroughly connected to earth by thick copper strips, which are covered with a layer of lead to protect them from acid fumes coming out of the stack. The strips pass down the outside of the stack. Here's one of the points at which the conductors are led down to a copper grid firmly embedded underground. This is the outside of a laboratory at UMIST, where very high voltages can be created artificially, so that, for example, electrical insulators can be tested to see how they stand up to a high voltage. We went there, however, to see a demonstration of artificial lightning, to see how well a lightning conductor works. Using special arrangements of capacitors, which can be charged up with electricity, a potential of 2 million volts is being built up. It can be applied to this single spike of metal, pointing downwards. 3.5 meters below, there's another spike, our lightning conductor, securely connected to a metal grid in the ground beneath. Watch. A potential difference of 2 million volts across an air gap of 3.5 meters causes the air to become conducting, and the electrical energy strikes to earth. Have a look at what happens when we freeze the picture for a moment or so. Conductor doing its job. A fine example of physics in action. Next week's Physics in Action program is the second on electrostatics. Teachers might like to refer to pages 7, 8 and 9 of the teacher's booklet.